Okay, so in today's video we're going to be making a start on the fourth area of study, which is probability and statistics. Now, as you know, this year this area of study has been reduced slightly. I am still going to record videos that in a truncated way talk through the elements, some of the elements of the course that were removed, purely because I think that actually they still add important background to some of the stuff that still remains in the course. So at those sections, I'm not necessarily going to insist that you do that exercise work, although I would suggest maybe just dabbling in a little bit of it just to get a bit of a sense of what's happening. But I will ask that you still kind of listen your way through that theory, just to give some background to what we'll then go on to, which will become important. So essentially, in terms of your textbook, I'm going to get my chapter numbers wrong off the top of my head here. Chapter 13, which is discrete random variables, is technically no longer in the course, and chapter 15, which is continuous random variables, is technically no longer in the course, and chapter 17, which is statistical inference, is no longer in the course. Now, we're all happy to see the rest of the chapter 17 gone. It was very frustrating when it was introduced, and we won't be going anywhere near chapter 17. Chapters 13 and 15, however, both offer important background to chapters 14 and 16, so I do think we need to touch on elements there. Chapter 13 is not completely excluded. The first exercises in chapter 13, which talk about probability more generally, they are still essential. So that is going to be the first two videos here that I will record. So let's get into it. So the first video is really just to build up some and to review notation around probability and understanding of sort of basic probability. Okay, so let's get into some things. So some terms and definitions and notations. So when we talk about probability, we talk about a probability experiment. Now that doesn't need to be people in a lab. It can simply be, you know, tossing a coin 100 times and recording the number of heads and tails you get, or whatever it might be. Standing on the side of the street and marking the colour of every car that drives past, or whatever. So essentially, you know, collecting the data really, I guess. So the sample space is the set of all the possible outcomes in the probability experiment. So if we were talking about the tossing of a coin, the sample space would be head or tail. Okay. However, if we're interested in the number of heads that we get when we toss the coin 3 times or whatever, then the sample space might be defined differently. So it's important that you understand exactly what the sort of experiment is measuring. You know, if we were standing by the side of the road and writing down the colour of the cars, the sample space would be red, blue, green, black, grey, silver, white, whatever, every possible car colour. Okay. If we are, for example, rolling a regular die, then the sample space would be the numbers 1 to 6. Okay, so set notation is going to be important in probability, and we use epsilon. There are some varying notations to talk about the sample space, so I wouldn't get too bogged down in the notation around sample space. Your textbook uses epsilon. So the sample space is equal to the set of numbers that contains 1, 2, 3, 4, 5, and 6. So 6 individual numbers. So it's important to understand that sample space is a set. Okay, so therefore set notations is going to be relevant in listing a sample space. Okay, so then an event is an outcome or set of outcomes that are of interest. So for example, we might be interested in obtaining an even number when a regular die is rolled. So we could call that event A, and therefore we could say that A, the sample space of A is equal to the set of elements that include 2, 4, and 6. Okay. If event B was obtaining a number greater than 3 when a regular die is rolled, then B would be the set of numbers 4, 5, and 6. Okay, so an event is essentially a subset of the sample space, a particular thing that we might be interested in when we're doing our probability experiment. Okay, so then in terms of how different events and sample spaces and whatever might interact with each other, we also need to review the ideas of union, intersection, complement, and mutual exclusivity when we're talking about sets. And we have talked about these things right back at the very start of the year when we reviewed our set notation in the context of domains and ranges. So we know that the union of two events is the set of outcomes in either or both events. So A union B is the set of outcomes that are in A or B or both. When we use the word or in mathematics, it's used inclusively. We talk about it being the inclusive or. So when we say A or B, we mean A and or B, okay? And that's always true in maths. So when we say A union B, meaning A or B, we don't mean either A or B, but they can't possibly be in both A or B. Anything that is in A at any point or B at any point is going to be in the union. The intersection is the set of all outcomes that are in both events. Okay, so the outcomes that are in both A and B, so we associate the intersection with the word and. We should be familiar with the notation for intersection. And so, for example, A intersection B in this case, let's go back to our example with the two events, where A is the outcomes 2, 4, 6, even rolling an even number, and B is the outcomes 4, 5, 6, rolling a number greater than 3. Then A union B is all of the numbers that occur either in this list or in this list. So 2, 3 is not in either, 4 is in both, that's fine, it's in the union, 5 and 6 is in both, that's fine, it's in the union, okay? When we talk about the intersection of A and B, it is the elements that are in both A and B. So that is 4 and 6. Okay. So remembering, Venn diagrams, it's the overlapping section. Whereas union, when we talk about union, if we were to draw, a Venn diagram of the sample spaces with A and B, the union would be everything that's in the either circle or in the intersection. The intersection of A and B would be the things, A and B, would be the things that are just in the middle. Right, then we can talk about the complement of an event, and that is the set containing all the outcomes that are in the sample space but are not in that event. So if our sample space is the numbers 1, 2, 3, 4, 5, and 6, and A is 2, 4, 6, then the complement of A, or not A, or A dash, is going to be 1, 3, and 5. The other thing to note here is that the intersection between A and the complement of A should be empty. So this notation means the empty set. So there should be no outcomes in the intersection of A and not A. Okay, that's because everything either is in A or not in A. And the other thing to note is that the union of A and not A should include the entire sample space. Okay, so for example, if we think about a Venn diagram, again, let's say we've got A and B, not A would be everything outside of here. So not just the stuff that's in B but not in A, anything that's not in A. And so therefore, if we were to combine together A, which is that, with not A, which is the black area, it's obviously the entire sample space. And then finally, mutual exclusivity. We'll come back to this when we talk more about independence in the next video, but two events are mutually exclusive if they have no outcomes in common. So that means if there are no outcomes in their intersection. So if you've got mutually exclusive events, when you draw their Venn diagram, you should be able to draw them as two separate circles because there is no overlap. There's nothing in common. Okay. So for example, I'll change that to C and D to be consistent with the information in the table. So if two events are mutually exclusive, I've already read that. So for example, if C was the set of elements of 1, 2, that are 1, 2, and 3, and D was a set of elements that are 4, 5, and 6, then events C and D are mutually exclusive. And they're mutually exclusive because their intersection is empty. So there's no specific notation for mutual exclusivity, but the implication of it is that the intersection of the two events will be the empty set. There'll be no outcomes in the intersection. Okay, some other notation. So probability, as you know, is a numerical measure of the chance of a particular event occurring. And when we write PRA in this way, we're referring to the probability of event A occurring. Okay. Some properties of probability. So probability of event A, we know is going to have to be somewhere between 0 and 1. If the probability of event A occurring is 0, it's impossible for it to happen. If the probability of event A occurring is 1, it's definitely going to happen, and probability can only be somewhere between 0 and 1. I know that seems really obvious, but a really important does my answer make sense moment is, have I got a negative probability or a probability that's bigger than 1? The probability of the sample space is 1, okay? One of the outcomes in the sample space has to happen. Otherwise, you haven't properly listed the sample space, because the sample space is the set of all the possible outcomes. So therefore, something in the sample space has to happen. Okay, if you do the experiment, the probability that what happens will be in the sample space is certain. The probability of the empty set, the probability of something that isn't listed in the sample space at all happening is 0. It's impossible for that to happen. The probability of the complement of A is going to be 1 minus the probability of A, and that's to do with the fact that the probability of something happening has to be 1, and then the probability therefore of A not happening will be the total probability, which is 1 minus the probability that A does happen. The final one is something called the addition rule, and this is, whilst it's a rule, and sometimes it's helpful to think of it as a rule, this is something that we all kind of do quite intuitively when you're working on probability problems, but we're going to formulate it here because it does come up. Can I just correct? Sorry, that's just a typo. That just should be a round bracket there. So we're talking about a rule for the probability of the union of A and B. It's helpful here to think about a Venn diagram. So if we have A and B, okay, and we're listing probabilities in the Venn diagram, we know that the union is everything in here. Okay, so what we can do is we could, to find the union, we could add up the probability of A and the probability of B, but there's a problem with that, because the probability of A would be the values in those two regions of the Venn diagram, and the probability of B would be the values in these two regions of the Venn diagram. And by adding A and B, we've counted the intersection twice. So the union is not just probability of A plus probability of B, because that's doubled up on the things that are in the intersection. So we would then also need to subtract the intersection. Okay. So as I said, that's actually quite an intuitive thing when you're working on problems, that sense, but it's important to have that rule in the back of your mind. Okay. One of the hardest things in probability problems is just organising the information into a way that it makes sense. Generally speaking, I would say once you have organised the information in the question, answering the probabilities is simple. Okay? The challenge is in formulating the situation, so in organising it in a way that makes sense. And we've got a number of organisational tools that are available to us in probability problems. Venn diagrams, Karnaugh maps or probability tables. These two things are the same. Sorry, I should have said or. There's a couple of others. I'll come to those in a second. But these two things are closely related. And generally speaking, any problem where you could use a Venn diagram, you could also use a probability table. One of the restrictions of the table, however, is that you can only be dealing with two possible events, A and B. You don't have more than two sides to the table to deal with. It's a two-dimensional thing. You would need some sort of cube to have a third event. Whereas the Venn diagram, you can add a third event and deal with probabilities. So that's one of the differences, okay? But if you've only got two events that you're dealing with, I would strongly advise use of a Karnaugh map or a probability table. And the reason for that is you get to include all the same information that you include in the Venn diagram. Okay, so what I want to be clear about is we've got 4 regions in the Venn diagram. This purple region, which is the intersection of A and B, in the probability table, we can display that here, the intersection of A and B. Okay. In the Venn diagram, this region out here is the intersection of not A and B. So this is all of the this is the probability that A won't happen but B does happen. That's in this cell in the Karnaugh map, okay, or the probability table. This section out here in your Venn diagram, this is all the outcomes that are in A but not in B, okay, and they're represented in this section of the probability table. And then finally, the region outside here is all the things that are neither in A nor in B, and they're represented here. So the same 4 numbers that you can put in the Venn diagram have positions, has places for you to put them in the table. The advantage of the table is that you also have somewhere to put your totals. Okay, so if you're told what the probability of A is, but you don't yet know how to break it up between how much of A is also in B or not in B, then you still have somewhere to put that value, and then you can work with it later. So given the choice between a Venn diagram and a Karnaugh map or a probability table, I would usually go for the latter, simply because it gives you positions in which to record the totals. The other really helpful diagram is the tree diagram. We certainly use that a lot. Less frequent is something like a lattice diagram or a table where you're just trying to look at the outcome of 2 different events. So we'll have a look at some different examples where we can utilise these diagrams. But as I said, work out how to organise your information according to making use of one of those tools, and everything after that will become pretty straightforward. Okay, as I said, let's just work through a series of examples. Example 1, a spinning wheel is divided into 8 sectors, each of which is marked with one of the numbers 1 to 8. The wheel is biased so that the probability of 6 is 9/16, while the other numbers are equiprobable. Okay, so we might not have seen that word before, but again, let's just think a bit logically here about what that might mean. Equiprobable, equal probability. Okay, so they have equal probability. Something else I should have mentioned earlier is that's important in probability problems is words like or phrases like selected at random, or an unbiased coin or an unbiased die. Okay, so this is a biased wheel. If it was an unbiased wheel that you're taking the spinner and dividing it into 8 equal sectors, pretend that they're equal. Okay, if it is unbiased, then the probability of each of those sectors, the spinner landing on any of those sectors, should be the same, and so each of them should be 1/8. Okay, what we've been told is the probability of so they're numbered 1 to 8. The probability of landing on the 6th sector is biased. Either it's weighted or perhaps the sectors aren't even sizes, so that this is 9/16. Okay, the probability of that happening is 9/16. So the first thing we want to do is calculate the probability of the number 1. So what we need to use is the fact that we know that the probability of getting a 1 plus the probability of getting a 2 plus the probability of getting a 3 plus the probability of getting a 4 plus the probability of getting a 5 plus the probability of getting a 6 plus the probability of getting a 7 plus the probability of getting an 8. That's the total sample space, so all of that has to be 1. Okay. Now what we know is that 1, 2, 3, 4, 5, 7 and 8 are all equally likely to happen. We don't know what the probability is, but it's equally likely. Probability of getting a 6th we know is 9/16. So essentially we know that 7 times the unknown probability plus 9/16 has to be equal to 1. So 7 times the unknown probability is 1 minus 9/16. That's 16/16 minus 9/16, so 7/16. And so therefore x is equal to, so this means that x is equal to 1/16. And so therefore, in terms of answering the question that was asked, the probability of obtaining a number 1 is 1/16. Okay. All right. If A is the event that a prime number is obtained when we use this spinner, calculate the probability of A and the probability of not A. Okay, so the probability of A is the probability of getting a prime number. Okay, so in this case, that is the probability of 2, so 1's not prime. Prime number is a number that's divisible only by 1 and itself. So 1 by definition, it's a bit technical, is not prime because it's only divisible by 1 or itself. Those are the same thing, and so it's not actually prime. 2 is prime, it's only divisible by 1 and 2. 3 is prime, it's only divisible by 1 and 3. 4 is not, it's divisible by 2. 5 is prime. 6 is not prime. 7 is prime. Okay, so the probabilities of each of these are 1/16. And so we've got 4/16 or 1/4. So then the probability of not A is the probability of not prime. So you could add up all the not prime probabilities just like we did above, but we also know the probability of A is 1 minus, the probability of not A is 1 minus the probability of A. So it's 1 minus 1/4, which is going to be 3/4. Okay, example 2. From a set of 18 cards numbered 1 to 18, one card is drawn at random. Let A be the event of obtaining a multiple of 3, let B be the event of obtaining a multiple of 4, and C be the event of obtaining a multiple of 5. List the elements of each event and then illustrate the 3 events as sets on the Venn diagram. Okay, so we've got that our sample space is all the cards, so that's all the numbers from 1 to 18. Okay, so event A is the event that we obtain a multiple of 3 when we draw a card. So 3, 6, 9, 12, 15, 18 are all the cards that are multiples of 3. Event B is the event that we obtain a multiple of 4. So that is 4, 8, 12, 16. Event C is the event of obtaining a multiple of 5. So that is 5, 10, and 15. Illustrate these 3 sets as sets on a Venn diagram. Okay, so we've got 3 events, so 3 circles to our Venn diagram. When you draw them, make sure that they overlap sufficiently so you've got space to write in them. And then you must also surround your Venn diagram with a box that's enclosing all of the sample space. Okay, so it's easiest to start filling out the Venn diagram from the middle. So are there any elements that are common to all 3 sets? No, so there's going to be nothing in the middle. Sorry, let me label them as, which might make that smaller circle C. So let's go with A, B, and C. Okay, so then let's have a look at between B and C. Is there anything in common? No, so there's not going to be anything in here. There's not going to be anything in here. Okay. Anything in common between A and B? So that would go in this region down here. So anything in common between A and B is going to be 12. Okay. Anything in common between A and C, 15 is common. Alright, so then we've filled in sort of the overlapping sections. So now the rest of the circle C will include all of the things that we haven't written in A and B, in the intersection between A and C. So we're going to have 5 and 10 out here. The rest of the circle A will be everything except for 12 and 15 that's in set A. So that is 3 and 6 and 9 and 18. And everything out here in B will be all the things that are in B that aren't already listed in any of the overlaps. So that's 12. So we're left with 4 and 8 and 16 out here. And then every element in the sample space should be listed in your Venn diagram. So anything that is not listed here is going to need to be outside. So I'm just going to count my way through the sample space. So the number 1 is not anywhere. The number 2 isn't anywhere. We've got 3, 4, 5, 6, 7 is not anywhere. We've got 8, 9, 10. We don't have 11 anywhere. 12, we don't have 13 anywhere. We don't have 14 anywhere. We have 15, we have 16, we don't have 17 anywhere. Okay, so we've got our Venn diagram. As I said, organising the information is key, then hopefully answering the other things should be straightforward. So part B is which events are mutually exclusive? Justify your response. Okay, so we can see that the important part to this question is the fact that there is nothing in the overlap between B and C. Okay, so the fact that there's nothing in the overlap between B and C means that, okay, so since the intersection between B and C is empty, B and C are mutually exclusive events. They have no outcomes in common. Okay, find the probability of A. So the probability of A is going to be the number of outcomes in A, so that's 1, 2, 3, 4, 5, 6 outcomes that are in A, divided by the total number of outcomes, which is 18, so that's going to be 1/3. Okay, then we want the probability of A union C. So that's all of the things, so probability of A union C, we want to count how many outcomes are in the union of A and C. So the union of A and C is anything in the A and C circles. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8 elements in there. So that is 8 out of 18, which is 4/9. Okay, so then we want to think about the probability of A intersection not B. Okay, so that is all of the regions of A that are not in B. So that is going to be everything out here. Okay, so that is 1, 2, 3, 4, 5 out of 18 things. So it's not 5 out of 6 things. Okay, that would be a conditional probability. We'll talk about that in the next video. It's just asking what is the probability that any element in the sample space is in the intersection between A and not B. And so there are 5 elements in that intersection out of the 18 elements in the sample space, or 18 outcomes when we're talking about probability. And then finally the probability of A intersection B intersection C, but not that. Okay, so that's everything that is not in the intersection of A, B, and C. So the intersection of A, B, and C would be this bit in the middle here, which means that everything that's not in that intersection is everything outside of that. Okay, so that's actually the entire sample space. Okay, that's 18 outcomes out of 18 outcomes are not in the intersection. So that's got a probability of 1. Okay, example 3. From a group of 42 students, it was found that 30 students studied mathematical methods and 15 studied geography. 10 of the geography students did not study mathematical methods. Let M be the set of students studying mathematical methods and G be the set of students studying geography. Draw a Karnaugh map to illustrate this situation. Okay, so in a Karnaugh map, we want to have sort of two sides to the table. They can be studying maths or not studying maths is the first side. And they can be studying geography or not studying geography. Okay. So from a group of 42 students, it was found that 32 students studied mathematical methods. So the total for maths methods is 30. The other bit of information, I should have put in, was that there's a total of we're surveying a group of 42 students. That's the total sample space. Okay. 15 studied geography, so the total for geography is 15. We don't know how many of those studied maths as well or didn't study maths as well, so we don't know how to break them down. And that's where if you tried to solve this problem with a Karnaugh map, maths and geography, okay, the first bit of information, you know that all 4 numbers are going to have to add up to 42, but 42 doesn't go anywhere in your diagram. The second bit of information, the fact that you know that 30 students study maths tells you that these two numbers add up to 30. 30 students study maths, tells you that those two numbers add up to 30, but the number 30 won't appear anywhere in the Venn diagram. The fact that 15 students study geography means that these two numbers will add up to 15, but the number 15 itself won't appear anywhere in the Venn diagram. So you've got 3 bits of information in, and none of them can go straight into your Venn diagram. And that's where, so particularly when you get information about totals, the Karnaugh map is so much more useful. 10 of the geography students did not study maths methods. Okay, so out of the 15 geography students, 10 of them did not study maths methods. Okay, so there's 10 students there, which means there's 5 that did. And again, then we can just start to add up the table. So if 30 students study maths and there's 42 students in total, then 12 don't study maths. If 15 study geography and there's 42 in total, then there's 27 that don't study geography. Okay. If there's 30 students that study maths and 5 of those also study geography, 25 of those don't study geography. And if there's 12 students that don't study maths and 10 of those study geography, then there must be 2 of them that don't study geography. So all of your, rows and columns should all add up to their totals. Okay, so once you've got, essentially you kind of need the total plus 3 bits of information somewhere in the diagram. Certain combinations you need to be a bit careful of that, and then the rest of the diagram can be filled in. So once again, now that we've organised our information, everything we need should be here in terms of answering the questions. So one student from the group is selected at random. Find the probability that this student, so at random, there's no bias, everything's completely likely to happen. That's an important phrase in the sentence. Find the probability that this student studies maths methods, but not geography. Okay, so maths methods without geography, there's 25 students out of the 42 students that study maths but not geography. So in terms of what we're going to write there, that is the probability that a student studies maths and they don't study geography. So that is 25 out of 42 students. If your fractions can be simplified, they must be simplified. But in that case, we're in simplest form. Find the probability that the student studies neither mathematical methods nor geography. So that is the probability that they don't study maths and they also don't study geography. So that is these 2 students here out of the total number of 42 students, because we're selecting randomly from the group of 42. So 2 out of 42, so that's 1 on 21 in simplest form. Part D, studies mathematical methods or geography. So remember, maths is inclusive or, so that means and or. What we're being asked for is the union between maths and geography. Now, I just actually want to go back up to the general Venn diagrams for a minute and the Karnaugh maps, just to be clear about what's happening here, the connection between these two. So we know if we're trying to find the union we're interested in everything that's in the circles, okay? So in the Karnaugh map, that corresponds to these three regions, these three cells here. Okay, so adding up those three numbers will give you the union. However, it's easier to notice that the union is actually everything except for this bit. So 1 minus the probability of the intersection of A and B would give you the probability of A union B. Okay, so in fact, 1 minus, or the sample space minus what's happening here will give you your union. Okay, so let's go back to where we were here. Okay, so if there's 2 students that study neither, that means that 42 minus 2, so 40 students must study either maths or geography out of the total 42 students. So that's 40 on 42, which is 20 on 21. Okay, example 4. 2 unbiased dice are rolled and the larger of the 2 numbers is noted. If the 2 dice show the same number, the sum of the 2 numbers is recorded. Okay, so we can use a lattice diagram here, but a lattice diagram only enables us to look at what combinations of numbers were rolled. What we're seeing in this particular problem is different things happen depending on the combination. So I'm going to set up a table, and I'm going to set up, let's try and do that. I'm going to set up a table where we have 1, 2, 3, 4, 5, 6. I'm just going to double that so you can be clear it's not a number in the table. So this is die 1. We could roll a 1, 2, 3, 4, 5, or 6. Okay, and then on the other die, we can also roll a 1, 2, 3, 4, 5, or 6. Okay, so there are 36 equally likely things to happen when we roll 2 die. Okay, some of those are repeat outcomes. Okay, so for example, the probability of rolling 2 3s is only 1 out of 36. The probability of rolling a 4 and a 2, we could roll a 2 and a 4 or a 4 and a 2, and so there are 2 out of 36 ways of doing that, so that would be 1 in 18. But you need to set up your diagram so that you've got each of the cells is equally likely to happen. Okay, now let's go back to the question because I'm going to fill in the table here what will actually be recorded if this thing happens. So the 2 unbiased dice are rolled. The larger of the 2 numbers is noted. Okay, so and then if the 2 dice show the same number, then the sum of the 2 numbers is recorded. So let's go down this middle diagonal, which is what happens if they roll the same number. So if they roll 2 1s, they add together the 2 1s, so they're going to get 2. If they roll 2 2s, they add them together. They're going to get 4. 2 3s, sorry, I nearly wrote 9, they add them together, they get 6. 2 4s, they'll record 8. 2 5s, they'll record 10, and 2 6s, they'll record 12. Okay, then everything else, when they roll 2 numbers that are not the same, they record the larger of the 2 numbers. So, for example, in this cell, if they roll a 1 and a 2, they're going to record 2. If they roll a 1 and a 3, they're going to record 3. A 1 and a 4 will be 4, 5, and 6. Okay, looking at the second row, here, if they roll a 2 and a 1, they'll record the 2. But here, if they record a 3 and a 2, it'll be the 3 that's recorded. Oh, sorry. It'll be the 3 that's recorded. 4 and 2, it'll be 4. 5 and 2 will be 5. 6 and 2, it'll be 6. Okay. Rolling a 1 and 3, you'll record a 3. A 2 and a 3, you'll record a 3. A 4 and a 3, you'll record the 4, 5, 6. Okay. A 1 and a 4, you'll record a 4. A 1 and a 2, it'll be a 4. A 1. Sorry, not a 1 and a 2, a 4 and a 2, it'll be the 4, 4 and a 3, it'll be a 4, 4 and a 5, it'll be 5, 4 and a 6, it'll be 6. Okay, and so we can fill in the rest of the table with the same logic. Okay, so that's our list of outcomes. Each of those things is equally likely to happen. Okay, so we want to find the probability that the result is a 5. Okay, so the probability that we rolled a 5, probability that we rolled a 5, there are, let's have a look, 1, 2, 3, 4, 5, 6, 7, 8 outcomes that result in a 5, so 8 out of 36. Simplifying our fraction, they're both divisible by 4, so let's go with 2 out of 9. The probability that we get a 10 in this system, there is only one 10 in the table. So the probability of getting a total of score of 10 is going to be 1 out of 36. The probability of scoring a number greater than 5 is going to be, so 5 is not greater than 5, so it means 6 or higher. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're also going to have 11, 12, 13. So those are all the scores that are bigger than 5. So it's going to be 13 out of 36. Which is in simplest form. Part D, the probability of rolling a 7. We can see that there is no way of getting, not rolling a 7, sorry, of getting a score of 7 in this system. There's no way of getting a 7, so 0 out of 36, the probability is 0. It's impossible. The probability, either a 2-digit number or a number greater than 6. Okay, so either a 2-digit number or a number greater than 6. So let's have a look. 2-digit numbers, we've only got 2 of those, and they're also greater than 6. So it's really just a question about greater than 6. 8 is also greater than 6. So there are only 3 numbers that fit in those categories. Okay, so 3 numbers that are both greater than 6 and, that are greater than 6 or are a 2-digit number. And they happen to also be both greater than 6 and a 2-digit number. So probability of 2-digit or 6. Okay, what did we say? It was 3 out of 36, wasn't there? So simplifying, it's 1 out of 12. And the probability of not a 9, probability of not 9 is, well, there aren't any 9s. So probability of not 9 is certain. There are 36 outcomes that are not 9s out of 36 outcomes. So that will be 1. Okay, again, take the time to organise your information, set up your table. Everything you need to answer any probability is then sitting there right in front of you. Okay, question 5. The 3:38 p.m. train to the city is late on average 1 day out of every 3. Draw a tree diagram to show the outcomes on 3 consecutive days. Okay, so thinking about what could happen. On day 1, the train could either be late or it could be on time. On day 2, the train could either be late or it could be on time. And on day 3, the train could either be late or on time. When you draw a tree diagram, make sure you start out wide so you've got room for your subsequent branches. Some people find it easier to draw tree diagrams that go out this way, okay, because it sort of gives you a bit more flexibility. And then sometimes they end up with tree diagrams that kind of start to become a bit circular, okay, but it does sort of potentially allow you. But if you start out wide as a general rule, then you should always have space to be able to continue it. Okay, so that's our 3 different 3 days. So we've got day 1, day 2, day 3, and what could happen each day. So over the course of the 3 days, we're now seeing there's actually 1, 2, 3, 4, 5, 6, 7, 8 different combinations of what could happen. Could be late, 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 could be late, late on time, late on time, late, late on time, on time. Okay, so we've got every possible combination represented here. What we also want to do is these aren't equally likely outcomes. So if you set up your tree diagram so that every branch is equally likely to happen, then at the end here the probability of each of these happening would be 1 on 8. However, they're not equally likely to happen because we know that the probability of the train being late is on average 1 out of every 3 days. The probability of a train being late is a third. So therefore, this tree diagram is weighted, and when that's weighted, we want to put the probabilities on the branches. So probability of being late is a third, therefore the probability of being on time is 2/3. So 1/3, 2/3, 1/3, 2/3, 1/3, 2/3, 1/3, 2/3. Okay. It's really important when you draw a tree diagram that anytime that you've got a set of branches emanating from the 1 point, the total probabilities have to add up to 1. If they don't add up to 1, you're missing a branch. there's a third option that could happen. Okay, so it's really important. If that happens, you just need to be careful about that. Okay, hence find the probability that the train is late on day 1. Okay, the probability that it is late on day 1 is simple, that's just a third. It's not affected by what's happened previously, it's just going to be 1/3. You could, if you want, calculate this probability, this probability, this probability, and this probability, which are all the different pathways by which the train is late on day 1, but if you multiply them all and add them all up, you'll still get a third. Probability the train is late on at least 2 days. So probability late at least twice. Okay, let's have a think about which outcomes is late at least twice. So that's going to be this branch, this branch, this branch, not that one, that's only late once. This branch, that's only late once, that's only late once, and that's late no times. Okay, so what we want here is going to be probability late at least twice is the probability that we are late, 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 or, so I want to be clear about when we use the word or in maths, we add. When we would use the word and in maths, we would multiply. So that helps you work with the tree diagram. So we want this outcome or, so plus this outcome or another outcome or another outcome, okay? And then we'll talk about each of those. I should have given us some more space here, sorry. So we can have probability late, late, late. We can have probability of late, late. I'm just going to write O for on time, okay? Plus probability of late on time late plus probability of on time late late. Okay, those are all the options. So for this to calculate each individual probability we want the probability that train is late and then late again and then late again. So we're going to be multiplying those probabilities together. So that is 1/3 times 1/3 times 1/3. The probability of late, late, and then on time is 1/3 times 1/3 times 2/3. Probability of late on time late is 1/3 times 2/3 times 1/3. And the probability of on time late, late is 2/3 times 1/3 times 1/3. So we multiply along the branches and then we add up the branches that we're interested in. Okay. Alright, so let's work this out. A third times a third times a third, that's 1 on 27. Plus this one will be 2 on 27. This is also 2 on 27. This is also 2 on 27. And this is also 2 on 27. So 2, 4, hang on, I've counted too many, haven't I? It's just 4 outcomes. So 2, 4, 6 plus 1, so that's 7 on 27. Making sure your final answer is simplified. Okay, the probability that the train is on time on the last day, probability of on time on day 3. Oops, day 3. Now, again, we're going to have 1, 2, 3, 4 outcomes. If we were to add all those together, though, it's a bit like the question about late on day 1. We would find if we multiplied all those branches and added them up, it would still be 2/3, because the probability of the train being late on any day is 2/3. Okay, so actually this one should just be 2/3. The probability the train is on time all 3 days, so on time, on time, on time. So one specific branch in the tree diagram is going to be 2/3 times 2/3 times 2/3. So that is 8/27. Okay, so some work to do here, exercise 13A. It's quite a big exercise. It's just really important that you really start to just explore a wide range of problems. A lot of the work in the probability is in the interpretation, in the, as I said, formulating an accurate diagram or representation from which you can then find the relevant probabilities.